Yep. Okay, so for the inverse, anything which is an inverse we can reflect in the line y equals x to find an inverse. So if I have, for example, if I have a sine goes like this and back the other way. Now if I reflect that, what I end up with is that light blue one. Alright, so inverse circular, that's alright, but this here says we want a function. Now this light blue one, what can you tell me about that in terms of it being a function? Or not? It's not, is it? Because a vertical line will cut many times. So it's not a function. So inverse, to get an inverse circular function, we then need to restrict the domain of our original. So if that one's sine x, to get the inverse of sine x, we can't take the whole sine x, we can only take a bit of it. And so that's what we do. We actually chop out that part and we chop out that part, so that when we reflect it, we now get something that's a function. Michaela, question. All right. So it's the same with cos and with tan as well. All right. So to obtain an inverse, we reflect in the line y equals x. And due to the cyclic nature of sine, cos and tan, we need to restrict the domain so that the inverse will be a function. Alright. All good so far? It's good that there's about a third of a page writing in my notes, and I've summarised it in that, is it? Alright, so let's have a look at them. Sine minus 1 is the first one. So when you see that there like that, sine minus 1, that's the inverse function. Alright, which is, in this case, it's not 1 over. Alright, it's not that. That's our reciprocal ones, which is cosec. Okay, so it's a little bit different than in other ways that we do work with other numbers, that in index of minus 1 there normally would mean 1 over, but for sine, cos and tan it doesn't. It means inverse, and the reciprocal ones are these other. So just be aware of that. All right, so sine -1 of x, we restrict the domain of sine x, and we restrict the domain to negative pi on 2 to pi on 2. All right. So that the inverse sine -1 is a function. Alright, so y equals sine x, where x is between minus pi on 2 and pi on 2, looks like this. So that's what that bit of the sine graph looks like.
Is that the sine graph? Yeah.
That's the sine graph. And I'm going to squeeze over here the inverse. So the inverse. So with the inverse, what's the other thing other than reflecting in the line y equals x? What else could we do? Swap the y and x, yes? Yep. So this point pi on 2, we have pi on 2 up here and minus pi on 2 down here. And 1 and -1. And so the inverse looks like, oops, that. It's a bit wonky in there. That's a bit better. All right, anything there that you want me to just go over again? No?
Have you swapped the y to x?
So when we reflect in the line y equals x,
Oh wait, yeah, I got it.
that gets reflected up and that gets so your x and your y. So if we were doing it algebraically, we'd swap the x and the y and then rearrange, wouldn't we?
Yeah.
So this end point up here, the coordinates of this end point up here is pi on 2 and 1. So when you do the inverse, those two have got to swap around, so it's 1 and pi on 2. Yeah?
Yeah.
All right. Now, there are other ways that the inverse is written. So, let's just write a note. Sine -1 x is also written as r sine x, arc sine x, and a sine x. Don't know why there's so many, but all of those four things all indicate inverse. And inverse reflection in line y equals x. All right, cos. So again, with cos, we kind of need this portion of the cos cycle. Again, so to get this portion, or something similar, where you're just going from your minimum to your max, or your max to the min, for cos we can just take this first bit here would work okay for cos. So for cos, we restrict the domain of cos x to 0 and pi. Alright, so y equals cos x, where x is an element of 0 to pi, and for cos, when it's 0, cos is 1, when it's pi it's -1, and pi on 2 it's 0, so we get that portion of it. It's a bit wonky there. So now when we reflect in the line y equals x, again swapping the x and the y, so that point down there is pi and -1. So then when we reflect that point, so over here we've got when we reflect this, excuse me, when we reflect this point, pi and -1, it's now -1 and pi. This point on the x-axis, it gets reflected onto the y-axis, and then here we've got this point here as on the colour. This point here was 0 and 1, so of course it now gets reflected to 1 and 0. And so we have these. Anything with that one?
So when you're sketching, like if you had to sketch both graphs in an exam or something, will you sketch them separately because you're able
Oh no, you can sketch them together, it's just the scales are going to be icky.
Right.
But you could sketch them together, yeah.
Okay. Is it better to sketch them apart?
Well, there's been a couple of questions on exams where there's a graph that's been there already, and then you're drawing the inverse on the one that you've already given in exam 2.
The scales are just like stuffing me up though.
Yeah, so you just have to do the best you can. So like that's 1, pi on 2, well what's pi? Pi is 3.1 or whatever. 3.1, so pi on 2 is about half that, so what's that, about 1.5 or something like that.
Yeah.
So you just have to...
So cos of the inverse of cos would be like going up to 3.1.
Yeah, that's right.
Yeah, okay.
Yeah, so, you know, you just have to do the best you can. So that's at 1, so, you know, this point here is going to be, it's going to be in there somewhere.
Yeah, right.
Right, so you just have to, you know, do the best you can.
Yeah.
Can do it.
Yeah. But yeah, you got to convert the pi to.
Yeah, so, you know, it's 1.5, so putting it out here, you know, this point, if you had it on the same graph and you're putting it out here, no, well, no, that's not. I mean, my scale's a bit out here, isn't it? That one's way too big compared to that, isn't it?
Is that stuff they're going to worry about?
Well, like I said, what I can remember is that with the mons, you've already got a graph, and they've already given you the axes with the stuff on it, and then you just do it. So they've already given you axes that are to the right scale. All right, and then you just go the decimal approximations and do the best you can do. And then what you would do, like if I did put that one on there, then what I would do is this point, I would have that point there, and then I would label it. I would label that point as 1 and 0. So if you're a little bit out with your scale, it doesn't really.
Yeah.
It's not a big issue because you've labelled it to say, well, this is what it's supposed to be. But yeah, like I said, if I put it out here, then that's not. As if that's at pi 2, which is about 1.5, and you're putting 1 out here. They will go, well, this person doesn't know where these numbers are supposed to be. All right, so of course with the cos you can have these cos. They don't use this one because there'd be 2 C's in a row, so that one's not used. Or a cos, the same. All right, tan. So again, we just need one wiggly bit from a tan, and the way that tan is with its asymptotes, essentially we just take a bit in between 2 asymptotes, because it goes like that. So for tan, we restrict the domain of tan x to negative pi on 2 to pi on 2. All right. So that's in between our asymptotes. There's one at negative pi on 2. There's one at pi on 2. And pi on 4 halfway is where it goes through 1. And minus pi on 4 is where it goes through minus 1. So there's our tan. All right, so when we reflect that, we're not going to get any repeating. So the inverse tan minus 1. So these asymptotes get reflected. So this one gets reflected up over here. This one gets reflected down here. So our inverse oops, that's not very good. asymptotes are there. Alright, and those other points, obviously it goes through the origin still. At this point that was pi on 4 and 1 is now 1 and pi on 4. And the other point that was negative pi on 4 and negative 1 is now negative 1 and negative pi on 4. So we get that. All right. Anything so far? Right, let's do some examples. No, 3, 2. All right, so here, sine minus 1 of root 2 on 2. So what do we know? We know that sine of pi on 4 is equal to root 2 on 2, don't we? Yep. So what that's suggesting then is that inverse sine of root 2 on 2 would be equal to pi on 4. Now, seeing as these things we're talking about as a function, what we then need to check is that this angle bit that we've got, this pi on 4 bit that we've got, that it actually fits into the domain we're looking at. All right, and so our restricted domain for sine was negative pi on 2 to pi on 2, and pi on 4 fits in that. So from that we say, okay, that sine minus 1 of root 2 on 2 is equal to pi on 4 then. Seems like I'm making something that's pretty straightforward, more complicated than it needs to be. However, we do need to make sure that the answer that we've got, because this is an inverse function that we're talking about.
If it's not in the domain, what do you do?
That's what we're going to get to here with this one. We've got to make sure that this number fits into that the restricted domain for sine. Yep. So with this one here, well, the answer we get, we've got to make sure that this bit that we give fits into that restricted domain for 10. And so that's what we'll have a look at now. All right. So for B,
Oh, is that it? You just got to write that it fits in the domain.
yeah, so this number that we put here has got to fit into the domain of.
But you don't have to sketch it or.
Don't have to sketch it, no.
Oh.
So the answer here is pi on 4. So tan minus 1 of negative 1 on root 3. And so our restricted domain is this. So for tan, our restricted domain is negative pi on 2 to pi on 2. So our final answer has got to be between negative pi on 2 and pi on 2. So what does that mean? Is for this, it's negative, so tan is negative in which quadrant?
The second and third. No, second and fourth.
Second and fourth. Now, because of this restricted domain, negative pi on 2 to pi on 2, the second quadrant's not even included in that. All right, so when I put those two things together, so we're looking for a fourth quadrant angle. Whoops. And the other thing about that fourth quadrant angle, we need to express it in a particular way. So, all right, because our domain's negative pi on 2 to pi on 2, when we go in the anti-clockwise direction, we can only go to pi on 2, so we can't. So what we've got to do is we've got to come back in that negative direction. So the fourth quadrant in the negative direction.
Wait, can you explain that again?
Our restricted domain is negative pi on 2 to pi on 2.
Yeah.
So if we've got a fourth quadrant angle, we can't go anti-clockwise because we only go as far as pi on 2 and we don't get there. So the only way we can get there here is to go in the negative direction. And that second quadrant one up here, well, we're not allowed, neither, doesn't matter which way we go, we can't get to the second quadrant because we can only go to pi on 2 or to negative pi on 2. Mm-hmm. All right. So, since tan of pi on 6 is equal to 1 on root 3, tan minus 1 of negative 1 on root 3 is going to relate to pi on 6. Pi on 6 is our reference angle, so that means in this case this angle in here is pi on 6, and we're going in a negative direction. So the answer there is negative pi on 6. Alright, again, it sounds like I've made something more complicated than it needs to be. Alright, but the thing is, out of this, the final answer we've got has got to be between those. Right, and as we know from what we've done previously, there's be lots and lots of different angles or that we could go to express, you know, second or fourth, But in this case, because of the restriction, we're only interested in the fourth, and then to get to it, we can only go in that negative direction. Okay? All right, let's have a look at this. Next couple of examples. Simplify.
Mr. Synno, what's under the pie?
3, sorry.
Thanks.
Oh, that didn't even look any better. There you go. Four, 6, 4, 4. All right, so simplify this. Sine minus 1 of sine pi on 3 and cos minus 1 of cos 7 pi on 4. Correct. All right. So, what do you think the inverse function and the function, what do you think they might do to each other? Cancel each other out, in effect. So, sine minus 1 of sine pi on 3, if they cancel each other out, that suggests that the answer is just pi on 3. Now, what you need to do is check our restricted domain. Alright, in this case it's negative pi on 2 to pi on 2. And then we need to say to ourselves, okay, does pi on 3 fit into that? Yes, it does. So our answer then is, so sine minus 1 of sine pi on 3 is equal to pi on 3. The next one, part B. So part B is cos minus 1 of cos 7 pi on 4 suggests, if they're cancelling each other out, that the answer might be 7 pi on 4. Our restricted domain however is 0 to pi. Now 7 pi on 4 is clearly not between those. So what we need to do is we need to figure out where else we might be able to find this angle. So 7 pi on 4. Oops. So if we're going 7 pi on 4, we're going around 1 pi on 4, 2 pi on 4, 3, 4, 5, 6, 7. So we're out here. what is, so that, excuse me, that's 7 pi on 4. And this angle down in here then is pi on 4. So really what we are now looking for is we are looking for an angle, excuse me, an angle between 0 and pi that will have the same cos value as 7 pi on 4. So the cos value of 7 pi on 4, if I make my triangle, oops, green, I'll make my triangle there, the cos value of 7 pi on 4 is positive. The other quadrant that has a positive cos value is the first quadrant. And what else are we looking at there then? This is our reference angle, yes, which is pi on 4, yes. So we know that the cos of 7 pi on 4 is the same as the cos of pi on 4. Now pi on 4 fits into this here, yes. So from that we could say that the cos minus 1 of the cos of 7 pi on 4 would be the same as the cos minus 1 of the cos of pi on 4. They'd be the same, would they not?
Yep.
So the final answer we're looking for is pi on 4. So in answer to your question from before, Toby, what do you do if it doesn't fit in your restricted domain? You look for the angle in our restricted domain that has the same as that cos, or tan or sine or whatever else. All right. A few more examples. All right, so those ones I just had the same function, but cos and inverse cos, sine and inverse sine. You may have an example where you have a mixture of those. So this one here, the cos of sine minus 1 of root 3 on 2. All right. So we'll work from brackets first. So sine minus 1 of root 3 on 2 is equal to what? Sine of root 3 on 2 relates to what angle?
Pi on 3.
Pi on 3 equals pi on 3. And for the restricted domain, pi on 3, that's in that restricted domain, so that's all good. So, cos of inverse sine of root 3 on 2 would then be the same as the cos of pi on 3, which is a half. So the only thing you've got to make sure is that when you do this first bit here, the angle that you use there is in that restricted domain. Because there's other angles as well that have a sine of 3 on 2, but they're not in the restricted domain, of negative pi on 2 to pi on 2. All right. Next one. State the implied. Alright, so state the implied domain and range of sine minus 1 of 2x plus 1. So just a reminder of what the sine looks like. Alright, so the sine looks like this. Oops. So this sine minus 1 of x looks like that. Alright, so the domain of this, so the domain of the inverse, not the domain of the sine, but the domain of the inverse is between minus 1 and 1. Yep. So the implied domain and range of sine minus 1 of this stuff. So what that suggests is that all of this here has to be between minus 1 and 1. Alright? For us then to be able to inverse it. So that's where the implied bit comes into. So negative 1, the 2x plus 1 is going to be between those. So then rearrange. Take 1. Divide by 2. So the implied domain of x for this function, sine minus 1, of 2x plus 1, x has got to be between minus 1 and 0. Right, for us then to be able to do the calculation.
So because it's between x, negative 1 and 1, oh wait, I've missed the number.
Because if you try to do the inverse sine of 2...
Hang on, why have you taken, so you got 2x plus 1.
Yep.
Negative 1 less than or equal to 2x plus 1, which is less than or equal to 1. And then you got negative 2.
So then I've added 1 to both, to everything. I've taken 1, I should say.
Ah, right.
And then I've divided by 2. So the x that goes into this has got to be between minus 1 and 0.
Yeah. That makes sense now.
All right, and the range, well, the range is actually pretty straightforward. So rather than you've got sine minus 1 of x, what does this stuff here do? It's,
Dilate.
yeah, shift, yeah, dilation, and then a translation. So dilate, translate. What does that do this way? Nothing. Yeah, that's right. So it doesn't do anything this way, does it? It's just dilate, dilate, translate. It doesn't do anything in the Y direction, so the range then is got to remain at negative pi on 2. So this is our domain. And our range will stay as negative pi on 2 to pi on 2.
Right. Will it always be the case that it will stay? Or just generally? Get a Y translation.
Here's I'm going to do an example here where I'm going to sketch something where it does change. Yep, the range does change. But in that case, all we've got changes in here is something to do with the x's, yeah? We haven't got anything in here that's got anything to do with the y, so yeah, there's no change for that particular one. This next one though, we're going to sketch this graph. Alright, so this one, there is going to be a change to our range. Alright, so I will show you a way that we can do it. Alright. So, as before, the easy, best way, in my view, is to start with our 2x here, which then leads us to our domain. And we know that the 2x has got to be between -1 and 1. Alright, so let's look at our domain. So our domain, 2x has got to be between -1 and 1. So that means that x divided by 2 here, x has got to be between -0.5 and 0.5. So, when we are drawing our graph, we're going to get that. Now, what do we know about, there's a couple of things, what do we know about what this negative pi on 4 does?
It shifts the graph.
Shifts the graph, correct?
Pi on 4 in the negative y.
Pi on 4 in the negative y. So for sine, so normally it's going to go through the origin there, yeah, and that's going to be shifted down. So that's going to be shifted down to negative pi on 4. So that's where it's going to go through here. These points here on the end point's always good to find end points. So how can I find those end points? Well, I can find those end points because those end points correspond to these spots here, don't they? So I can say when x equals negative half, so f of negative a half is 2 lots of sine minus 1 of negative 1 minus minus pi on 4, and then do some calculations. So a sine of -1 corresponds to what angle? Negative pi on 2? Cancel there, negative pi minus pi on 4, which is minus 5 pi on 4. Down there. Happy with that? Hope so. And then over here, that's when x is a half, f of a half do a couple of things in a couple of lines in the head there. You get 3 pi on 4. Which is up here. And there's our graph. Anything about that? So rather than working out the range in that particular case, what I've done is I've worked out my endpoints, and now from my endpoints I can work out what my domain is, rather than various other ways you could do it. But that's as good as any. All right. Anything about that? No. All right. That's it. Exercise 3C stuff.